All right, we live? Thank you, one person. All right. Let's get started. Hi, everyone. My name is Zac Sweers, and I currently work at Nowhere. Today, we're going to be talking about an open source dependency injection framework that I built called Metro. I published my slides here. Going to stall time for a little bit in case anyone wants to take a picture, tell you a little about myself. Formerly worked at Slack, Uber, and Flipboard. I've authored a few Dagger party tricks blogs and talks. Been a past contributor to a popular extension of Dagger called Anvil, an author of a KSP fork of it called Anvil KSP. I'm also the author of a few compiler plugins that will become relevant later in the talk. At Slack, I tech-led some projects you may have heard of, like Circuit and Compose Lints. And in my free time, I like running, soccer, and fostering dogs. So before we get started, quick poll around the room. Who here uses like Dagger plus or minus Anvil? It's most of the room. Who uses anything else? Okay, decent amount. Anyone not use DI, like at all? Do you write tests or? Kidding. All right, so if you're not familiar with dependency injection, I'm going to call it DI for the rest of the talk. Fear not, we're going to start with a little bit of a primer. So what is dependency injection? So first, let's look at an example. Consider a simple weather app. It's basic. You give it a location, and it gives you the forecasts for that location. Our weather app is composed of a few components: a weather service class that can talk to a weather API, a weather formatter that can format responses into a localized format friendly to the user. It's simple. It prints the formatted forecast for a given location when we run it. So in a trivial implementation, we may just take these and make them into properties of the class. Now, you can probably already see some problems here. Maybe our weather service is used in multiple places. We are a weather app, after all. A popular pattern for this becomes the singleton. So it's just as hard to test, but at least now we're limiting instances. If we want to make this testable, though, we have a few options. Maybe we set some set service backdoor into our test. It's powerful, but prone to leaks. If you have multiple levels of this, though, it pretty quickly becomes unwieldy. Suddenly, they're also surprisingly mutable. And you, the consumer, have to know quite an awful lot about how these dependencies are wired, and only fails at runtime. So maybe we move to using a service locator instead. This could be as simple as get application.getWeatherService. Get application could be any type of service holder. So by injector.instance or by inject or the locator framework of your choice. Locators, though, are still hard to test because you do have to still backdoor it in somewhere. And what's worse is that they're, again, only validated at runtime if they're validated at all. If you're handwriting these especially, you're probably not doing any of this validation up front. So the last and best option is to just make your dependencies a constructor parameter. This doesn't even technically need a DI framework to use it, and is often just called manual DI. In manual DI, we just deal with simple constructors most of the time, and if you know the language, you understand the code you're reading. This is a textbook example of the programming concept called inversion of control, or my preferred description, the Hollywood principle. Don't call us, we'll call you. So aside from the standard language features, the kicker here is that you don't need to know where that dependency comes from or how it's wired up above you. In a test, you just new it up. If you want to fake the data, give it a fake weather service. There we go. Scoping in this case is not the responsibility of the consuming class either, which helps with setting this up in a test. And it's implicitly validated at compile time because you literally cannot compile it if you don't pass these dependencies down. You're not having to go fish things out of a bag at runtime. Manual DI isn't free, though, because we still have all this boilerplate wiring somewhere, and it scales up pretty quick, too. Your service likely needs an HTTP client, which likely needs some sort of cache, and this is where DI framework comes in. So without further ado, we want to dry this up and introduce Metro. So, Metro is a compile-time dependency injection framework that draws heavy inspiration from Dagger, Anvil, and Kotlin Inject. It tries to unify their best features under one cohesive solution while adding a few new features along the way, and it's implemented as a compiler plugin. So why another DI framework? So I feel like it's felt for some time like the Kotlin community has been waiting for a library that kind of unifies the best of Dagger code gen, multiplatform, Anvil's aggregation, things of that nature, and you want IDE support. A lot of people write custom lint checks for this. And you want it to be sort of Kotlin first, like Kotlin Inject does, whereas Dagger generates Java and is often pivoted to be Java first, or positioned as Java first. Different solutions exist for different parts of these, but I don't think that there's been a cohesive compile time solution that sort of unified and checked all these boxes. It's also a lot of domains that I've worked in, and I guess at some point I decided that was me in the middle. So in short, Metro basically stands on top of a lot of stuff that came before it. It doesn't seek to reinvent the wheel in this, and instead tries to build on top of what was already working well and smoothing over stuff that could have been better. The idea, hopefully, is also a one-stop shop, so you don't have to think about 3, 4 different frameworks that are all working together. So to start using it, all you need to do is apply the Gradle plugin for it, and you're on your way. Metro builds on top of established patterns from existing DI frameworks with familiar semantics, such as different injection types, providers, multi-bindings, scopes, and some intrinsic runtime types like provider and the Kotlin standard libraries lazy. Like other DI frameworks, Metro lets you use annotations to indicate dependency semantics in your code directly, allowing you to replace this wiring with just this. The primary entry point here is the dependency graph. All you need to do is define types or type keys that you need, and it'll manage these instances for you. Metro's compiler plugin will implement it at compile time, following dependencies from their roots. Graphs, in this case, are analogous to Dagger and Kotlin Inject's components. Creating a graph is quite easy. It's using a magic typed create graph function. This is what we call a compiler intrinsic, meaning that the source is just a stubbed body, and the compiler actually comes and replaces this call at compile time. So it's similar to the standard library's typeof function if you've used that. If your graph itself has inputs, you can create a factory interface annotated with @dependencygraph.factory with a single abstract function that takes any input parameters and returns the graph. Parameters must be annotated with either @provides or @includes. Provides annotated parameters will be directly available on the graph as a simple instance parameter. Includes we'll get to later. And then you can just call create graph factory, another intrinsic, and the compiler will replace this with a call to the created factory implementation. So how do we get other bindings into this graph? So if you the simplest way to provide a binding is what's called a provided binding. It's an overly simple name, but it's just a function on the graph that we annotate with @provides. And this can return whatever type you want to stick onto the graph. That type is then available to anyone else on the graph. Provided bindings can also have dependencies. We just add them as parameters, and Metro will stitch them together accordingly. Providers can also be inherited from supertypes, allowing you to define common interfaces and reuse these in different graphs as needed. If you want to provide multiple instances of the same type, you can disambiguate them with something called a qualifier annotation. So qualifier annotations are meta annotations, meaning they are annotations that go on other annotations. A convenience built-in one is called @named, and that just takes a string argument. The pair of a binding and type and its optional qualifier is what we call a type key. And Metro views every binding on the graph as a type key. What is a binding? Inside Metro, each type key on the graph is modeled by what we call a binding. We've covered one type, this provided binding, and we'll cover a few more in a bit. Binding, in this case, is a managed instance that we have keyed by its type key, and a dependency is any binding that is depended on by another binding, and more about the relationship between the two. Most of this talk will talk about things in terms of bindings. Now let's look at how injection works. So if you own the class, you can actually skip provides and just annotate the class directly. The typical way that you would make a class injectable and available on the graph is to just annotate it with these @inject annotations. In simple cases, you can just put them directly on the class itself. If you have multiple constructors, you can also annotate a specific injectable one. This, in turn, is another binding type we call a class binding. Now, this gets us pretty close to our original sample. And in this trivial example, this alone isn't saving us that much code. Where a framework like Metro or Dagger or Kotlin Inject, et cetera, really shines is where its native features start making the tedium easy. So let's do that, starting with scoping. So like Dagger and Kotlin Inject, Metro supports scope annotations. These indicate the scope or the lifetime of a binding, and it must match the graph that they attach to. That is to say, this tells the compiler to ensure that only one instance is ever created for the lifetime of the graph that it's included in. So first, our graph must declare its scopes. These are also meta annotations, and Metro's standard scope annotation is just @in, which takes what's called a scope key k-class argument. Metro also supplies a common app scope key class. Sorry, word soup on these. And these combine to make @in app scope, and we just stick that onto our app graph. In is lifted from Anvil and is essentially Metro's analog of Dagger and Kotlin Inject's @singleton. It's a little more explicit about the scoping, since singleton in this case really just means singleton within that graph. So I preferred this name rather than offering a first-class singleton annotation directly. Note that our graph also declares scopes. We can use scope, and this is required in order to use scoped bindings within that graph. Going back to our example, scoping the weather service, like we needed before, is now actually just as easy as adding a scope annotation directly onto our class. The scopes are a single instance within the lifetime of the app graph, and anything in the app graph or its extensions will always get the same lazily initialized instance of our weather service. So, like Dagger, all bindings and graphs are unscoped by default. Scoped bindings are lazily initialized with thread-safe, doubly checked locking. There is no single check or reusable option in Metro. There's an FAQ about it, but basically it boils down to not feeling like it was super necessary. Scope is declared at the binding site rather than the consumer needing to know about it. And certain binding types can't be scoped, and we'll mention those as we go through them. So we've covered class and provided bindings. One unique thing that Metro can be private. So in source-based code gen like Dagger or Kotlin Inject, everything that the compiler generates has to be able to access whatever type it's invoking. So your constructor or your provides function, which means that they need to at least be package accessible. Since Metro operates as a compiler plugin, we can actually modify the code directly. So let's cover the remaining binding types. Next up is an optimization called @binds. Just like Dagger, these are callables that are like aliases. They're just a simple abstract function or extension property that act as a pipe to say that this binding is actually just an alias to some other binding. Metro never, or as such, they must also be type assignable. Metro never generates any code for these declarations and uses them purely as compile time signal. Since they're just an alias to their alias type, they also can't be scoped independently of it. This is something that Dagger allows. I found it a little bit complicated to do it and wanted to keep scope in the original site. Common use cases for this include binding implementation types as interfaces that they implement, binding types into multi-bindings, we'll get to that in a bit, binding types as nullable variants, because Metro is Kotlin first, it also understands Kotlin nullability as a first-class feature, and you can also bind types to other types with different qualifiers. Next, let's talk about assisted injection. So in some cases, you may have a class that requires a runtime dependency to be instantiated. So for example, consider an injected user repository that needs to know about a user ID in order to be constructed. We could put this ID on the graph, but it's not really something that we need on the graph. We may also want to create multiple user ID or user repositories for different IDs. So to support this, Metro has something called assisted injection. And to do this, you mark which parameters are assisted with this @assisted annotation. And then we add a simple factory interface annotated with @assisted factory that has a single abstract function with matching assisted parameters. We also disambiguate these injection types with a slightly different inject annotation. Instead, we use @assisted inject. And that's valuable for the compiler to know when we're using these types that we can't actually depend on them directly, but rather that they have an associated factory that we should be using instead. These parameters in the assisted factory must match the constructor's assisted parameters, and this SAM function must return the assisted type. And with this, you can now inject this factory, and Metro will generate code to handle shepherding the assisted parameters to the constructor injected type. The last major binding type is multi-bindings. Multi-bindings are just collections of bindings that are aggregated either into sets or into maps. Contributing is easy. We just annotate a given provider or class binding or binding with either @into set or @into map. The underlying binding on the graph for the final collection is created automatically if any of these into annotations are present, but you can also declare them directly with an @multibinds annotated declaration in your graph. The Metro compiler will implement these getters as well, so you can just call them directly. One notable difference from Dagger is that Metro will error by default on empty declared multibindings, and you have to opt in to allow empty ones. For map keys, the keys must be statically defined at the binding site with a map key annotation. Map keys are the final meta annotation that we have in Metro, and you can define custom map key annotations with it. There are, again, some built-in ones here like class key, string key, etc. If you have a collection you want to contribute into a set, for example, another set, you can also use @elements into set to contribute them all at once. Next, let's talk about aggregation. So who here uses Anvil or Dagger Hilt? So good, 50% of you or so. So Metro has Anvil-style binding aggregation built in as a first-party feature. What this means for those not familiar with Anvil or Hilt is that you can basically slingshot contributions or bindings from some other module to a destination or component or graph that you want to host those bindings. With it being a first-party feature of Metro, there's no needing to have intermediary like @merge component annotations or anything similar, nor do these tools need to try to preempt the graph generation by running at some earlier stage of the compiler or the build. So for example, Anvil had to work by operating in the capped stub generation step so that it would get a chance to run before Dagger's annotation processor could run. Aggregation works by what we call aggregation scope keys. These are actually the same keys that you would use with something like @single_in, allowing for some shared semantics. And this is the Metro way of saying aggregate all bindings contributed to this scope. In fact, if you declare an aggregation scope, then you don't actually need to include this @single_in because Metro will actually treat it as implicitly added for this case. So what's a contribution? Well, there's three types. The first we want to consider, say you have a graph that wants to expose a cache. And this cache is an interface, and we have an injected implementation available. Metro can discover this automatically. It is annotated with @inject. But the automatic discovery here is technically just a cache impl type, and we need a cache type. So we could add a @binds property in our graph, but we already know at the implementation site that we do want it exposed as a cache type. And this is where we introduce our first contribution type, which is an annotation called @contributesBinding. So contributes binding contributes @bindings for that class as one or more of its super types. Under the hood, Metro is going to be generating a contribution interface that the consuming graph just ends up extending. If there's multiple super types or an ancestor type, you can also explicitly define it. If you're familiar with Anvil, this works mostly the same, except that the bound type is a little bit more flexible. Metro uses this binding semantic here, and that actually allows us to store generic types. We can put qualifier annotations in here. It's not limited to just being a K class. Again, things that we can do since we're a compiler plugin. The compiler will validate all of these at compile time, so that the annotated type extends and implements the bound type, and if it doesn't, it will tell you, and you don't have any surprises. If you have just a single super type, you can also just omit the binding argument altogether, and we'll understand that you're just implicitly using that type. Now, if we want to contribute into a multi-binding, we can do that too. Contributes into set contributes in a class into a multi-bound set of its super type. Maps are similar. We just annotate the class with the map key as well. The third and simplest type, or contribution type, is something called @contributes_to. So maybe we define these handlers in some other interface, and we just want to make sure that the app graph eventually extends this. Contributes_to just contributes the annotated interface to that scope, and then the graph will end up extending it in the final compilation. As long as these classes are visible on the class path to the graphs that declare that scope, the Metro compiler will automatically aggregate and include them directly in the graph. This is super useful, if not necessary, when working in a larger modularized code base. Next, let's talk about intrinsics. So, like Dagger, Metro supports injection of bindings wrapped in what we call intrinsic types, namely provider and lazy. These are useful for deferring creation and initialization of dependencies. They only need to be requested at the injection site, and Metro's CodeGen will generate all of the necessary stitching to fulfill that request. Provider is like Dagger's provider. It's a simple interface whose invoke call will just return an instance every time. If the underlying binding is itself scoped, then it's always going to return the same instance whenever you call invoke. If it's not scoped, then it will return a new instance every time. Lazy is just the Kotlin standard library is lazy. It lazily computes a value the first time that it's evaluated, and it's also thread safe. Note that lazy here is different from scoping in that here it's confined to the scope of the injection site rather than the graph instance itself. There's functionally no difference between injecting a provider or lazy of a scoped binding. The underlying implementation in Metro's double check prevents double memoization in that case. The last thing I want to cover in this sort of prolonged primer is something called graph extensions. If you're familiar with Dagger subcomponents, this is the same concept, but with a hopefully more obvious name. Graph extensions are graphs that extend other graphs, and you declare them with this @graph extension annotation, and then declare an accessor for them in their parent graph to tell Metro to generate them. Like regular graphs, graph extensions can also have factories that you can declare instead. The parent graph can also implement these factories. They can have scope annotations, they can have aggregation scopes, they can have provider and binds callables, and they can also even have their own chained extensions beneath them. Okay, so that was a long primer. Thank you for sticking with me. There's a bunch of neat advanced features that I'll touch on at the end, but I want to pause here and return back to our original example. So let's hop on the build train and follow how Metro runs these tracks in the compiler. First, let's look at a conventional Gradle build pipeline. In the simple case, you just have a compile Kotlin task, and if you're in multiplatform, you'll output multiple binaries. If you run KSP, then KSP is going to end up running first and generate some sources that go into compile Kotlin. And this is sort of what, like, say, the Anvil KSP or Kotlin inject pipeline generally looks like. If you run capt, you actually get two precursor tasks, one Kotlin compile task to generate Java stubs, and one Java C task to run Java annotation processing over those stubs. Then its outputs are piped into the compile Kotlin task. If you have any Java sources, you also get a compile Java with Java C task after your compile Kotlin task. And in a complex case such as Dagger compiler, you can end up with 4 stages in your compiler here. So stubgen, capt, compile Kotlin, and because Dagger generates Java, compile Java. So that's 2 Kotlin compilations and 2 Java compilations. If you use Dagger Hilt, its Gradle plugin actually adds another Java C task at the end, so that gets you up to 5. If you run KSP, that is somewhere in there. And, you know, you got 6. There's a lot happening here, and I don't have room on the slide for a 6th anyway. And that's just one module. So in a modularized code base, this gets multiplied by n number of modules in your project. And this obviously isn't ideal. Large teams will try to mitigate that impact by limiting how many modules, say, like apply capt. This is also a big appeal of Anvil, which allowed you to offload some of this work that the Dagger compiler was doing by its factory generation feature. In Metro, all we ever have is just one compilation. This alone makes it much faster than the above scenarios. And on top of that, it generates IR directly in the compiler, so there's no round trip to generate sources and then compile those. How much faster, you may ask? Well, it's pretty fast, like up to 40 to 70% faster, depending on your setup. There's a benchmark project in the repo and also some shared testimonials on the documentation site. But I encourage you to obviously measure and test for yourself, too. So let's explore the phases of this compiler. There's 2 primary phases in the Kotlin compiler. We have the front end and the back end. Each of these have roughly 2 interphases with a translation layer in between. Let's break these down in order and what Metro is doing in each. The front end is focused on parsing sources, reporting diagnostics, and building a resolved front-end IR, aka FIR, representation of the Kotlin code that is ready to be compiled. It's a tree structure representation of the Kotlin code that it parsed. So source files go in, the parser reads these files and loads a PSI representation of them. That's the same PSI that runs in IntelliJ, the same PSI that runs in lintchecks, or that lintchecks are built with. And this is sort of basic tokenization to build an FIR tree and shakes out things like syntax errors. Once the FIR is constructed, a wealth of checkers actually run over this tree to report diagnostic issues, like literally just hundreds and hundreds of these in the compiler. And because FIR is what's running in the IDE, they show up in the IDE. FIR was introduced in K2 to streamline the compiler front end and significantly improved compiler performance along the way. It also unified the model that the compiler and the IDE ran, making it much easier to introduce new language features. So if you felt like things had sort of slowed down leading up to K2 and things have sped up a bunch since K2, this is a big part of why. The front end is also pluggable. So in K1, there was something called analysis handler extension, which I'm not going to cover here, but it's worth mentioning that that's what Anvil and KSP were built on top of and why it was much faster than using capped factory generation at the time. This hook was really only for generating new sources, though. Even in Anvil's case, it would generate new sources and then run the front end again for multiple rounds. And it also didn't support custom diagnostics, as far as I know. In K2, there's a fully fledged plugin system for generating new declarations, transforming them, adding custom checkers, etc. And Metro uses all of these. Metro does 3 types of mutations in FIR. We've got declaration generation, we have super type generation, and we have something called status transformation. Metro generates a lot of different types of declarations. Constructor-injected classes or providers get generated factories that graphs call to create instances. Here we end up getting another benefit of Metro. Since we can modify classes and generate classes within them, this is what allows us to inject private constructors, since nested classes can access the outer enclosing classes' private declarations. Assisted injection needs to generate factory implementations. Contributed types generate a nested contributor interface that will host binding declarations, et cetera, graph creators, member injections, a few other things run in here. Most of these declarations implementations are generated later in IR, but in order for them to be visible across modules, they need to be visible to Kotlin metadata. And in order for classes to be visible to Kotlin metadata, they need to be visible at the end of FIR. So we generate header signatures for these classes in FIR, and then we go and implement them in IR. In the IDE, you can also see these generated declarations if you enable IDE support. Supertype generation is a callback that we get during FIR construction to generate additional supertypes onto a given class. This is the hook that we use for Metro's aggregation features. Skimming over the implementation details a bit, but it allows us to tell FIR that these classes should be supertypes of our final graph. Even though these classes may not be implemented yet, just denoting their supertypes is enough to satisfy the compiler here. And a neat new IntelliJ feature is that it'll show these contributed supertypes in the IDE as well. And you can actually even skip doing, say, like SmartCast. Finally, we have status transformers. Status in Kotlin is this batch of modifiers in a declaration. It also includes modality, think like open, final, and sealed, and visibility. Metro has two transformers. The first transformer transforms provides to always be private, allowing you to write them without a visibility modifier, but transforming them to be private at compile time. The second adds an override modifier when necessary to an accessor if it was contributed by a supertype that has a matching signature on one of its accessors. FIR generation is extremely finicky because FIR has life cycles. Remember, this is running in the IDE, so you don't actually know here if, say, a function that doesn't have a return type is intentional or if the user just hasn't written it yet. Metro, as a result, tries to limit what it does here to just the bare minimum. It even does have some features that rely on IDE visible FIR generation, but they're behind flags because it's still sort of new and up and coming in IntelliJ itself. After FIR generation is done, we enter the checker phase of FIR. So checkers are basically helpers for reporting diagnostics to make sure you're holding it right. Think things that are syntactically valid but programmatically wrong. A simple example of one of these is to make sure the dependency graph factory has a single abstract function. That function must return the dependency graph, and that function has to have valid parameters. Metro has nearly 100 diagnostics of this type to make sure that you don't accidentally do the wrong thing and try to bounce you in the right direction. Since this is all in the front end too, they appear really fast and early in the compilation. And again, since FIR also runs in the IDE, these show up right in the IDE. Full IDE support requires a bit of setup, and there's documentation on the doc site. But once ready, it can show diagnostics and even show you generated types like generated assisted factories. I'm going to race through because I am running up against the clock here, and there's other people coming in. So now let's talk about the backend. So up to this point, all Metro's plugins have done is create basic headers for the classes and merge contributions. Now we're getting to the fun part, graph generation and graph validation. The Kotlin compiler backend speaks a structure we call IR, and an FIR to IR phase runs to convert FIR trees into IR trees. In the backend, we then have two phases. IR transformation, where transformers transform IR code across multiple rounds to optimize known programming patterns or generate extra IR code. And then there's an IR lowering phase, which lowers IR code into target platforms like the JVM or native, JavaScript, etc. Each supported platform has their own conversion to their binary format. Metro doesn't do anything in IR lowering, so I'm going to skip right past that and only focus on transformation. At a high level, IR transformation could be thought of as like the implementation details of the compiler. This is the phase that implements the bulk of the code, ranging from desugaring language features that we like to more primitive constructs, optimizing common patterns into more efficient alternatives. It's also a fair bit older than FIR, having gone stable in Kotlin 1.4 or 1.4.3. This is also the phase that Anvil's contribution merging ran in. However, in K2, it's no longer possible to run this in cap stub generation, which is why Anvil is never going to work in K2 with Dagger. Metro's IR transformation runs in two parts. First, it finishes generating those binds functions that we generated in FIR for contributing types. Along the way, we collect some information about all the contributions. And secondly, it transforms everything else. At a high level, I apologize, this graph, or this slide is not very readable, but breezing through here. At a high level, Metro's pipeline in this phase can be described as transform non-graph classes, so simple mechanical implementations for things like factories, and then processing dependency graphs, which goes in order of collecting graph data, like information about its bindings, roots, extensions, etc. Processing any extensions first so that we can know if they are using any scoped bindings from the parent graph. Building a binding graph. This is the graph data structure within Metro that holds bindings and can validate them. Sealing that graph, which populates bindings starting from the parent's roots, as well as any that the child graphs asks for. Running a hybrid targen plus con algorithm to detect cycles, safe cycles, and perform a topological sort of the resulting bindings, and produces a result at the end with your sorted bindings, the reachable ones, and any deferred types for valid cycles. If the binding graph is valid, then we start implementing the IR graph class directly from it. My clock says 0. How am I doing? Thanks. I'm going to try to go through as quick as I. Go quick? Yeah, all right. All right, so let's go back to our weather app here and see how they're modeled in IR. First, we're going to peel off metadata from the graph, things like the scope, any bindings, etc., accessors. Then we're going to end up plugging this in to a binding lookup so we can go find them. Then we start walking from roots. I'm really breezing through here. Once we have a list of all the bindings that we populated from that visit, we plug them into Targen's algorithm. This is basically for doing cycle detection, and it gives us nice, clean error reports whenever we have a cycle. If that all passes, then we take the resulting bindings that we have left, plug them into Con's topological sort, which tries to sort them, you could think of as the safe order to initialize them, starting with dependencies that have 0, or bindings that have 0 dependencies. Once we've got all of our bindings available and we're done sealing the graph, we can start implementing the actual graph. So to decide what fields we need, we have this provider field collector class. Scoped bindings are usually the only things that need fields. Any bindings that are reused, we'll toss into a field for reuse as well. If they're scoped, we wrap it in a double check so that we only ever get one instance, and then the rest of it is just calling through those like generated factories that we had. And then we will go through at the end and implement any accessors for the final graph, and then there we go. Then we have a functional working graph that looks really ugly on here, but the point is you don't have to see it because it's compiler generated. There's some other stuff that I'm not going to get into. There are considerations we have to make for incremental compilation. There are hooks in the compiler for doing this. Metro uses those hooks. It makes it very fine-grained. We also do transformations for these create graph calls that I mentioned at the beginning to turn them into real calls. If validation fails, we try to give you really readable and actionable information, including hints at the bottoms of messages where appropriate to say, you know, hey, like you asked for this, I couldn't find that, but I found one that looks similar. If you have a cycle, it'll also tell you information about the whole cycle. If you have invalid bindings, we have other types of hints to tell you, you know, hey, like this is probably not what you meant to do here, and this is probably what you wanted instead. This is everything I didn't have time to talk about today. Hi, everyone at the door. Adoption, there are docs, you can go read them. Custom code generators, also possible. Migration, also possible. FAQ, also on the doc site. In the future, also on the issue tracker. Thank you, goodbye.